Right. So, yes, we had talked about thermodynamic variables and okay. So we spoke about intensive and extensive variables in the last class. So I think you guys have a fairly good idea about uh, what these properties are. So extensive properties, are something which depend on the amount of matter, and intensive properties are something that actually don't depend on the amount of matter that is present in the system. And some of these examples are pressure, temperature, density, refractive index, molar specific heat. Those are intensive properties. And the extensive properties are like volume, heat capacity, energy, surface area, mass, and then things like that. And there's another aspect that, of course, you can control, you can change the extensive properties into intensive properties by suitable normalization. This is going to be very important in the sense that uh, these intensive properties actually determine uh, um, the thermodynamic processes. I'll just give you a context. You know that there is uh, the size of Indian economy. The GDP, if you will. It's I don't know the number. It should be about $3 trillion or something, right? But you compare that thing with the GDP of Switzerland, for example, you'll see that the GDP of Switzerland is fairly low. Okay, talk about the total numbers of it. But then, if you consider the GDP per capita, you know, the amount of business transactions happening, monetary transactions happening, normalized by the number of people that are there. And the same thing you do for India, and you'll see that Switzerland is far, far ahead than India. I'm just taking Switzerland as an example. It can compare it with the United States or Pakistan or Bangladesh or France or any other country. So that GDP per capita actually gives you a fair idea about the state with people do their daily lives, or their buying capacity, or what kind of sort of life they have, and what kind of life expectancy, what kind of educational opportunities they have, what kind of you know research or development opportunities they have. So that gives you a fair idea. Although the total GDP, if you count the total GDP of the country, it doesn't give you a very clear idea about what's the state of people there. So that's why, and it's a very abstract example, just to give you a context of what a normalized parameter can give you. The same thing you can compare with buying a stock where things are available and gross, and what's the price of it vis-a-vis what is available individually and what's the price of it, and you will see that sometimes per unit price is lower, and that's where people go to buy stuff, right? Anyway, coming to typical thermodynamic processes, where, and what I said in the last slide is applicable here, defining a term called equilibrium. Okay, equilibrium is sort of at rest. Things are not moving, things are undergoing no changes, and all the thermodynamic coordinates are kind of constant. They are there. Okay, if you look about a bookish definition of that, which is perfectly well planned, well written definition, this is what is written here. If a system is left to itself, the thermodynamic parameters have a tendency to be uniform throughout the system, right? And then the steady state condition reached after that is called equilibrium, when all the thermodynamic parameters are kind of uniform throughout the system. And any other thermodynamic parameters are changed, then the system is considered to be undergoing a process. Something is happening. Process is something is happening, right? And in that process, let's say one parameter goes through several steps and then comes back to its original step, comes back to its initial state. Then it is said to be undergoing a cyclic process. It sort of completes a cycle, right? And likewise, you can talk about many different types of processes where some of these common examples are where temperatures stay constant, volume stays constant, pressure stays constant, and some of those examples are given here. When you talk about an isothermal system, thermal meaning the temperature, although we'll discuss about what temperature is. Uh, in an isothermal system, the isothermal process, temperature stays constant. An isobaric process, bar is sort of referred to pressure. Isobaric process is where pressure remains constant, and then you have isochoric process where volume remains constant. Right. Now, talking about pressure, pressure is it's defined as force per unit area. You can calculate any kind of pressure that you might experience. P is F by A. And, and the most important point is what I've been talking about, is that any difference, any change in the pressure is what leads to a process. Okay, and if pressure is throughout equal in the system, it sort of remains constant in the system, then it will be called that the system is in mechanical equilibrium. All right. Now, if you look at the cartoon here on the right, then here is a two-chamber gas chamber system. You have say for ideal purposes, you have a frictionless movable wall. And in this situation where you have a high pressure here and there's a low pressure here in this gaseous chambers, then what's going to happen is that this high pressure is going to push the piston into this region so as to equilibrate the pressure. Okay, and would come to a state where you have in both the chambers equal
Hello.
pressure. Yeah.
Hello, sir. Sir, slides are not visible actually.
Slides are not visible?
Yeah, we are not able. Yes, sir.
Oh, okay. Hold on a moment. You should have said that earlier. Okay. Well, hold on a moment. We'll do that. Slides are not visible. Oh, okay. I haven't shared the slides. That's the problem. Okay. Now. Okay. Is it visible now?
Yes, sir.
Yeah,
Yes,
yeah,
sir.
yes, sir.
All right. All right. Okay. Okay.
It's
Okay. So we'll
visible.
go over again.
Mm.
So yeah, I think we have done this, and these are some of those definitions and all that which talked about. And yeah, this is the slide we were talking about. All right. So yeah, well, let's go over again. So these are the two system. It's a system where there's two chambers. In these two chambers, in the left one here is high pressure, and it has got the frictionless movable wall, and this has got low pressure. And as we said, the pressure needs to equilibrate. And that's the gradient. If you look at it, is the P1 which is higher and P2 which is lower, and there is a difference between this P1 and P2. And over it, if you calculate the distance over which there is a pressure difference, you typically term it as pressure gradient. The change in pressure happening over the change in some distance. That is pressure gradient. We will talk about that at some point. So here, simply speaking, the system would undergo a process wherein these difference in the difference in pressure that's existing here would be eliminated through a process, and it will establish a situation where this chamber 1 and chamber 2 would have another pressure which is equal in both the cases. Okay, like again, if you change the pressure here, if it becomes high pressure here, then this piston wall is going to move to the left, and thus establishing equal pressure. And it's very important in the sense that this pressure, the difference in pressure, the equality of pressure would lead to an equilibrium that's called mechanical equilibrium. So you see that pressure is a quantity that's related to mechanical equilibrium, right? And there's so many ways you can calculate pressure, and some of these are scientific units, some of these are engineering units. Some of these are laboratory units, and it's all the same. It can sort of, these are interconvertible, just that usage wise some people use it in different places. Bar and atmosphere, 1 atmosphere is what we always experience while we are outside, and 1 torr is one pressure unit that typically people use for vacuum industries. Millimeter of mercury is something that we use all the time. It's sort of equal to atmosphere when you take a proper 760 millimeter constant multiplied there. And of course, in the British units, you have PSI, and that also was an engineering unit. And at some point, it continues to be a unit, but then gradually we've converted to SI units, which is System International units, and you should be able to convert this. And this is for you to work out what is a pound. PSI is pound per square inch, so that you can convert to kilogram per meter square or kilogram per millimeter square, and some of the units also are kilogram per centimeter square, depending on what kind of materials you're talking about. So that's what is pressure. And then going about, this is the macroscopic definition of pressure. If you go back to the microstate things, then you realize that you can calculate pressure of a gaseous ensemble by calculating how many numbers of atoms are there, and then what kind of force they exert on each other. And then you sum it up all together, and you'll be able to figure out what the pressure is. And you'll see that what we measure on a gross scale is actually equal to what calculation you might do based on the first principles. Okay. Then again, another important term comes, which is temperature. Sometimes it looks like it's futile to discuss about that, but then you need to have a sense of temperature when you talk about thermodynamics, and a very good sense of it is required. We generally say that it's the temperature which determines the direction of flow of heat, right? And again, it sort of started with perception. If you touch a hot body, then you feel heat, and you feel the hotness of it. So in a way, a lot of people would have said that it's the degree of hotness that's there in the body, and that tells you about temperature. It's not wrong. It's not very wrong. Uh, but then that's again a relative term. It's a relative term. So if you touch a glass of water which is warm, which, let's say, 45 degrees Celsius, then you'll feel the heat. But then if you touch ice cold water, or chilled Coca-Cola, or lemonade, you'll see it's cold. But does that mean there is no heat in that 0 degrees Celsius, or 4 degrees Celsius lemonade, or a Coca-Cola bottle? That will be wrong to say that there is no heat. There is heat. Just that we, being at a body temperature of 37 degrees Celsius, we see when we touch a lower temperature, we feel that it is cold. So it's a relative term that gives you the perception, but that relative term is important because it determines the flow of heat. So when I touch something which is a 0 degrees Celsius, and I touch this, then heat has to go from here to here. That's a very everyday example. Likewise, this could happen with engineering as well. So likewise, what we talked about in the pressure case, here you have two chambers, gas chambers or liquid chambers, or the two solids in contact with each other, and there's a diathermic wall which can allow heat to pass. Then you'll see that this high temperature and low temperature containing substances would eventually form an equilibrium, and that will be called thermal equilibrium. And this temperature here is going to be different than this temperature or this temperature. And most likely, it is going to be a temperature somewhere between this and this, thus establishing thermal equilibrium. So a change in pressure, or the equality of pressure, establishes what is called a mechanical equilibrium. The equality of temperature actually establishes something which is called a thermal equilibrium. Right? And likewise, when you talk about chemical equilibrium, it's the equality of concentration throughout that establishes a chemical equilibrium. I haven't got a slide for it, but then I can give an example. Well, let's say you take a glass of water and then you add a drop of ink, right? Ink is why I say ink. You could say even sugar or salt or something, but the ink is where you can actually see what's happening because it's got a dye and its diffusion you can easily mark, you can easily observe. So in that sense, if you drop, if you place a drop of ink, then you see that gradually from a very deep color, it converts to a slightly mellowed or a lighter color, but then eventually in some time, in a few minutes, it establishes the same equal color throughout the body of the water body or whatever container you had. That means that the color actually is a representation of the concentration, meaning the number of molecules of that dye or the ink per unit volume of the water. So you'd see eventually that the whole body, whole system has equal concentration of the dye, thus giving a slightly purple color or a blue color depending on what ink you have put. But there is no gradient in the color. Whereas when you first dropped it, there was a huge gradient. You know, everything else was a clear water, and then when you had dropped, it's intense blue or intense violet, of the intense color of the dye that you had put. Okay, but eventually it comes to a complete equilibrium, and that we can call that it's in chemical equilibrium in the sense that the concentration of the dye that you put, it's equal, the unit concentration is equal throughout the volume and thus establishing chemical equilibrium. And just to wrap up what we have had here in temperature, you know, the measurement of temperature is by itself a wonderful subject, you know. Uh, I think every engineer should read that, not for academic purpose, but you know, as a purpose of general knowledge as to how people have started measuring things. You know, the most important part of engineering is measurement. You know, anything that is there that can be felt or you know can be seen, anything that is there has to be measured because that's how you standardize. You know, when you say things, when you say things in a standardized manner, it actually communicates very clearly. So that standardization came with the reference point of freezing point of water, right? Because it's so prevalent in anywhere in the world that it becomes kind of easy to understand, taking that as a basis. The freezing point of water or melting point of ice, that becomes the basis, and then we kind of take things from there. Turns out, and that was what is called a Celsius scale of measurement. You know, I think we are all familiar with it. You know, and that's not an absolute scale. That's only a relative scale where we have put 0 degrees Celsius as 0 degrees Celsius, the melting point of ice as the baseline, and then we've said positive temperatures from that and negative temperatures for that. But then gradually the absolute scale was figured out where it was seen that 273.16 Kelvin, you know, that the unit is Kelvin, that is connected to 0 degrees Celsius. Freezing point of water is 273.15. The triple point is taken as 273.16. That's, you know, there's a difference between 0.01 between the triple point and the melting point of ice. Triple point is something where, you know, all those three phases come into equilibrium, meaning water, ice, and vapor can coexist at the triple point temperature. So, and you can do a simple calculation. Celsius scale is the Kelvin scale minus 273.15. So when the important thing is that I think all of you should bear in mind and do it, sort of do it, practice every time, is that when you do numerical calculations, you cannot use a relative scale, which is Celsius. You can never use Celsius. it has to be an absolute scale, and that has to be in Kelvin. Okay, and what else? Yeah, I think we talked about it. And then there are other scales also, like Fahrenheit, which is still used in the US, although we use for normal everyday temperature measurements and all that, or what is there in the atmosphere, or today is hot or cold or something, a bad day or a nice day, we sort of define everything in the sense of in Celsius, right? We don't do that in Kelvin. But then if you go to the US, even Celsius is not in use. They always say that it is in Fahrenheit. So that's, they use pounds, they use miles, they use Fahrenheit. So that's a different thing. But that's on the daily life thing. When you talk about scientific substances, you got to use it on absolute scale. And the absolute scale, which actually tells you one more thing also, is that there is only zero. That's absolute zero. This minus 273. That's absolute zero. Anywhere else there is positive temperature. There's nothing called a negative temperature. Okay, only the change in temperature can be negative. That's del T can be negative, but T can never be negative. All right, so these are the things. These are what do you call rules, the thumb rules. You can never say that the temperature is negative. All right, of course, only when you define it in Kelvin on the absolute scale. Right. Okay, so now coming to the zeroth law of thermodynamics, which is an interesting one. Sometimes it's felt that it's so trivial, but it's not quite trivial too. Um, and that also is related to temperature and thermal equilibrium. So we said that thermal equilibrium is established when temperature is constant in throughout the system, right? And zeroth law was actually making a basic sort of formulation of equality of temperature, and that leading to thermal equilibrium. And it is prevalent in the sense that across bodies, across systems, and if you, to put it into words, it is two systems in thermal equilibrium with a third are in thermal equilibrium with each other, right? So if there are two systems, A and B, where A is in equilibrium with C and B is in equilibrium with C, that would mean that A and B are in equilibrium also. And in totality, you'll see that A, B, C all are in equilibrium. That means that all of these three systems possess the same temperature. Okay, that this is something which defines the concept of temperature, and that's the starting of measurement of temperature, and which is called thermometry. Okay. Interestingly, as a historical fact, the zeroth law was sort of made or sort of recorded long after the second law and the first law. And see if it comes in the reverse order, and the second law was the first law to be sort of adopted, which was followed by first law, although developments with regards to the first law of thermodynamics and the second law of thermodynamics were actually happening simultaneously. But nevertheless, second law came first, and then the first law, and then they put a law which was sort of felt that it's actually the foundation, the basic thing. So they didn't find any number; they put a zeroth law into it. Okay. It's not that there's not much to learn about it, other than the fact that temperature is the driving force, right? Uh, Before that, let's go back to one of those concepts of intensive properties. So we talked about we talked about pressure, we talked about temperature, and we talked about composition, right? And we talked about processes and equilibrium. You'll see a common chord here, in the sense that it's only the equality of an intensive variable which is actually establishing equilibrium. If you look at it, see, pressure or equality of pressure establishes mechanical equilibrium. right? And pressure, you see, is an intensive property. Establishment of equal temperature leads to thermal equilibrium, and temperature, as you know, is an intensive property. Equality of composition establishes chemical equilibrium, and the composition, when you define composition is some composition per unit volume, then that becomes an intensive property. So it's a profound theory. It's well, it's sort of, these are the things we observe, and then it becomes very easy to understand that it's a driving force. Okay, these are the intensive properties which are driving forces, which actually makes the process to occur. And there's no gradient in these driving forces. That means if the driving forces are equal, in a way, in other words, if the intensive properties are uniform throughout the system, then it's more likely that there's going to be equilibrium in the system. And this is such a generic thing that you can perhaps think about anything, about any system, and whether they are in equilibrium or not, you can sort of guess or predict by looking at some of these intensive properties associated with that particular system that you're talking about. That is something I didn't know while I was an undergrad, like in your place. I hope if you put this into your mind, understanding many of the systems would be fairly easy for you. Sort of, it gives you a formula, it gives you a clue that if you're considering a system, look at what are the intensive variables that are affecting the system. And if those intensive properties or intensive variables are uniform throughout the system, if they're not, they're probably in equilibrium, not in equilibrium. If they can be made equal, perhaps you will be going to be establishing equilibrium, right? Okay. So now we'll talk about the basic gas equations. I don't think we need to spend much time in that. So, excuse me. So you have Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's principle, and then you have combined gas law, and all of it are something that you've already done. So Boyle's law is, PV is constant. Well, of course, you can keep the temperature and the number of moles of the composition constant, and that gives you some sort of a curve like this, where you plot the pressure and the volume, and you see that these curves are, like this, almost touching in the axis, but not quite touching it. These are hyperbolic curves. And the effect here is that when you increase the temperature, this is for T1, this is for T2, this is for T3, and then as you increase the temperature, the curves are going to be shifting slightly away. And you can do a lot of calculations depending on, for this point, you can draw the pressure coordinate and the volume coordinate. For this one, you can draw the pressure coordinate and the volume coordinate, and things like that. And this is going to be useful when we talk about work in subsequent classes. Likewise, Charles talks about the variation of volume and temperature. It of course constant pressure and constant with the forest given moles of substances, and you see that volume and temperature are sort of proportional to each other in the sense that the ratio is maintained. Likewise, Gay-Lussac's law is talks about the relationship between P and T. Gay-Lussac's law is not widely known. It has got a different name also. I just don't remember exactly that. Of course, that tells you about the relationship, much like the B and T. It's the P and T relationship, um, with of course a constant volume for a constant set of number of moles. And then the Avogadro's principle. Avogadro principle is, it sort of connects between the volume and the number of moles that you have for a particular pressure and temperature. I think you might know that. The Avogadro number is the magic number. 6.023 into 10 to the 23 is what we talked about while we're converting between macroscopic properties and microscopic properties. And that number, it has an essence of converting a single molecule to a molar number of 1 mole of molecules or 1 mole of atom to a single atom. That conversion it makes, and says that the volume is actually proportional to the number of moles that you have in the system. And all of these things combined gives you the ideal gas law. It's not the it's not the real gas law, but the ideal gas law, meaning like typically it sort of applies in at low temperatures, and these are the laws where we have we have not, or we don't consider the interatomic attractions and things like that, which is a profound law, PVs and RT. That's for all purposes of calculations within the domain or within the scope of this subject. We'll be using PVs and RT unless, of course, otherwise stated, right? And likewise, these are some of those variations that you might see. And if you plot P versus the inverse of volume, it will give you a straight line. And on the other graph, you see that P and V gives you a hyperbolic line. And likewise, this is Charles' law, whereas a volume and temperature plotted, and then it gives you straight lines for that. And of course, you could see that if you decrease pressure, the thing moves to the left. And you can think about, when you decrease the pressure, it's going to go towards the volume side. All right, you can feel it. Think about it. In a gas system, you want to see the change of volume and temperature, and you do it at one temperature, one pressure, and then you reduce the pressure, and then do the same once again, and you'll see that it's following the same linear relationship, but it's going towards the higher volume side, right? Because the lower pressure is going to go into higher volume side, right? Could someone please switch the microphone off? There's some noise coming out. Right. Likewise, you'd see that on the Gay-Lussac's law for this, there's pressure here and then temperature here, and then of course there's a linear relationship. And much like this, when you, instead of here you have volume, you have pressure here. Of course, temperatures are the same, in the x-axis. Here, if you decrease pressure, all right. Okay, can someone please switch off the microphone? There's a lot of noise coming. Yeah, so the same linear relationship holds, just that when you decrease the system volume, it's going to go for a higher pressure. So compare the same linear relationship applies, but then when you keep on increasing volume, it's going to the slope is actually turning towards higher pressure side. So that is something we can actually feel ourselves. And from here also, you can see P into P versus 1 by V relationship. If you increase the temperature, that's going to go towards the pressure side. So this is a representation of what we have been talking all along. The PVT representation in a three-dimensional form, three-dimensional coordinates, and this surface is actually gives you all the possible states with. And this is what? This is a locus or loci of all the points for different pressure, volume, temperature combinations. All right, it's nothing exotic. Just that you have pressure as a variable, thermodynamic variable, volume as a thermodynamic variable, and temperature as one more, and then all of these things will take possible states, possible numbers, depending on how they change. And then if you have to plot all of those things for different pressures, for different volumes, or for different temperatures, you'll see that all of those points connected give you this kind of a surface. This is the surface of possible states within the domain of the combined gas law, right? And that, if you go slightly deeper into that, if you take a pressure slice, if you take a cut, okay, and the cut is what? This is the plane, this is the cut, okay, and that cut is made on it at some pressure, right? That means throughout this region, okay, in the three-dimensional field, and you talk about the same in this region, the surface, it will come out as a line, and this is the line which is representative of only one pressure. That means pressure doesn't change here, right? So that's going to be an isobar, okay, and that's going to be an isobar. Then you see the relationship between volume and temperature being proportional, and that's representation of Charles' law, right? Likewise, you'd see, let's say we talk about an isochore. That means you fix the volume in that three-dimensional block. Let's say we are fixing the volume. Volume is this point, and since it is three-dimensional, into this line. So if you follow this line, okay, if you follow this line, it's going to be. Can I get numbers? Can I get? No. The pens and all that, where it is available. Anyway, we'll do that later. So if you look at this one, this plane, if you take a cut, if you take a volume cut, meaning here is one volume and then you cut inside, you take a slice of this. That is the surface where, in the three-dimensional block, that is the surface where volume is constant. In that, if you talk about the surface of all possible states of PVT, then this is the line where volume stays constant. So this line would be representative of something which is called an isochore. Isochore meaning volume is constant. And within that, in this line, pressure is going to be proportional to temperature. That's simple. That's Gay-Lussac's law, right? And likewise, of course, if you take this one, isotherm, take an isotherm. Isothermal system, meaning this is the temperature scale. This is the temperature scale, and here this is if you take a cut of this is where temperature is constant, and temperature is constant is an isotherm, and that isotherm to be represented on the surface of PVT as a line like this. It is just simply this cut, and when it interacts, this whole surface is what is outlined here. This is the isotherm. Okay, this is the line. This is the isotherm where temperature remains constant, and of course here PV is going to be constant. So it's as simple as that. Just and a different three-dimensional representation of all the possible states, all the possible coordinates that you the scenario of PV, right? Of course, when you convert the ideal gas behavior to incorporate real happenings, then you sort of change the ideal gas equation by putting in some corrections, which are one is on the pressure correction and one is on the volume correction. That, and this law is the real gas law is defined here for 1 molar system, and the idea of pressure correction comes because in the kinetic theory of gases we hadn't talked about the container wall effect. When we talk about calculation of pressure, only from the impinging forces, collisions from different molecules, we had completely neglected the kind of collisions the molecules would make on the container wall. Okay, when that is taken into consideration, it sort of came out that the pressure would slightly increase, and it'll increase by A by V square amount, where this A is sort of defined as the critical pressure related to A by 27 V. So these two constant A and B, and this volume correction comes just simply by the excluded volume. You have set of number of moles of gases wherein the one molecule experiences the volume of the whole less its own volume. All right. So that is taken by incorporating a slightly negative term in the sense that the available volume is slightly lower than what was taken in the ideal gas law. So that kind of gives you um, subtle corrections, and of course is equated to RT. So that's it. So we have kind of come to the end of the basics, although the basic would still continue, but in more on the thermodynamic terms. Uh, so 2 minutes, huh? More on the thermodynamic terms that will continue. We talk about different other parameters which are not used to the gas, simply the gas laws and all. We talk about internal energy, we talk about enthalpy, we talk about work. So by and large, we'll talk about different thermodynamic elementary processes leading up to the formulation of first law of thermodynamics in the subsequent classes. All right. So today, let me stop here and then take questions if there are any. All right. Okay. Let me. I'm sorry. Okay, it is still. I don't know. Yeah. Can you guys hear me?
Yes, sir.
Yeah. Okay.
Yes, sir.
Now,
Yes, sir.
yeah. So tell me if there are any questions. Any more questions? Any
No, sir.
difficulties and all that? Of course, we are just warming up. I mean, we'll have more serious discussions going forward. These are just the basics. So I think most of the things you might have known already. Uh, but I hope that should be reflected in answering questions that I might set it in some, um, assignments or online tests or things like that. I can understand if there are no questions. Right. Okay. So should we close today? Okay. If there are no questions, let's meet. Let's meet next week. Right.
Yes, sir.
Yes,
Thank
sir.
you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you.
Yeah. Thanks.
Thank you.
Thank you.